Hello and welcome back. My name is Dr. Mark Taylor. This is the Delaware Tech Physics 111 Lesson 7, Part 2. Lesson 7 is the fourth lesson of Unit 2 on forces and energy. We started with types of energy, and in this video we'll continue with how we represent them with various bar graphs and other types of diagrams. So we're going to introduce you to the LOL flow diagram, energy pie charts, and energy bar graphs. And in an LOL diagram, these are diagrams that are actually named after the shape of the diagram, not after any specific abbreviation. And I'll scroll down so you can see exactly what I'm talking about here. The very bottom diagram, it's a collection of three diagrams, an L diagram, an O diagram, and an L diagram. The L diagram is a graph, and you can see the axes of the graph look like an L. The last one also is a bar graph where the axes look like an L. And the center diagram portion is a circle looking like an O. That's why they're called LOL diagrams. So the initial energy state of a system is represented by the first bar graph. You basically see a variety of bars that are labeled with different types of energy. And in this case, there are four spaces for bars, though only one bar is represented here. The bars are kinetic energy, Ke, gravitational potential energy, GPE, elastic potential energy, EPE, and non-mechanical energy, NME. So those are the four spaces, and the bars represent how much of the energy is in each of those forms. And we'll get to that diagram in a minute. But let's just take a look at the last one is also another bar graph, and you see the energy is distributed in a different way. And in the center is this system flow diagram, which is basically just a circle. Inside the circle represents all the things you count as the system, and everything outside the circle is everything you don't count as a system, what we call the surroundings. So the surroundings might bring energy into the system, or the system might bring energy to the outside surroundings. And those methods of transferring energy could be things like work or heat. Mostly it's work that we discuss here. Occasionally we'll mention heat. So that's the LOL diagram. And in this particular example, our system is composed of Biff, a balloon that Buffy is throwing at him, and the Earth. And Buffy is standing high up on a ledge, Biff is down on the ground, and there's a water balloon that Buffy is tossing, and it lands on Biff's head. So we have a number of different things happening at various times in the process of Buffy throwing the water balloon, it going up, it coming down, it hitting Buff's head, it exploding on his head, and spraying water everywhere. So let's look at the various steps and the energy involved in each of these. And I'm going to scroll down a little further to what's known as a stacked bar graph, and it's color-coded with far more detail than we'd ever expect you to know. But I want to show this to you to show you how energy changes from one form to another throughout the course of some event. But these labels here, it's important to know what these labels are. In red, it's gravitational potential energy. And you'll notice that in the very beginning, all of the energy is in gravitational potential energy because Buffy is holding the water balloon up high. She's not changing, but where the water balloon goes is. So we're going to focus mostly on the water balloon and its contents. In yellow is the kinetic energy of the balloon. In blue, the elastic potential energy. In purple is the internal energy. So this includes thermal energy and the various molecular movements with the water as they're flying around and eventually landing on Biff's head. And then we have in green the kinetic energy of the droplets because the balloon is going to break and spray water. In gray, we have something called surface energy. You're not responsible for knowing what that is, but that energy refers to the surface tension of the water. And as the water is being broken up into droplets, that energy is being released. And then in brown is acoustic energy, which we're just going to call sound. And you'll see that at every moment in time, the distribution of the different types of energy is changing, but you'll also notice that the amount of total energy at each moment in time is the exact same total. It's 100% of the energy, and that energy is conserved, so the total doesn't change with time. It's just the homes where the energy is located in each step of the way. So initially, all the energy is gravitational potential energy. We're looking at number one. Because the balloon is elevated and at rest, there's no motion, no deformation of the balloon. She tosses it, so immediately after she tosses it, there's energy shared between the gravitational potential energy and a little bit of kinetic energy, because now the balloon is moving and the balloon is dropping down, so it's losing gravitational potential energy, but it's gaining kinetic energy. And in number three, the energy consists again of the gravitational and kinetic. We have still more kinetic as it's falling. And in the fourth state, just before impact with Biff's head, there's significantly more kinetic energy. Now, if this was landing on the ground, eventually almost all the energy would become kinetic energy, but it's landing on Biff's head, and Biff's head is about 5 to 6 or more feet above the ground. So there's going to be some gravitational potential energy even after it hits his head. If we look at step 5, the balloon and the head are compressed. In other words, the balloon is impacting his head. It presses his head. The balloon gets pressed, obviously, more than the skull does. And the energy is a mix of kinetic energy of the water, maybe a little bit of Biff's head, elastic potential energy because of the stretching of the balloon, internal energy from the molecules of the water now being transferred to internal energy of Biff's head, because some of this energy is going over, and Biff's head might be slightly deformed in the process. The balloon is definitely deformed in the process. In step 6, we have even more of an impact. The balloon totally shatters, and now we have some surface tension energy. We have the sound of the impact, so that's acoustic energy. The internal energy from the water balloon is dispersed, and it goes with the water droplets, and some of it goes into Biff's head. And then by state 7, the final state, which is a little while later, that internal energy has had a chance to stop, and the energy has spread via heat throughout the surroundings, and the remaining energy is a little bit of gravitational potential energy, because a lot of the water is still on Biff's head, which is a bit above the ground. So we have this constant shift in where the energy packets are located, but the total always stays the same. And you're not responsible for the details of this. This is just showing you how we analyze the changes in energy using a stacked bar graph below. And then in terms of the LOL diagram, if you look initially, the left bar graph, all of the energy, and I'll point to that so you see it, all of the energy is in the gravitational potential energy. But by the end, it's distributed. Some gravitational potential energy, some kinetic energy of the movement of the water. So at this point, we're really at this stage. We haven't waited till all the heat has been spread around. But there is a significant amount of internal energy and sound energy and deformation energy that goes into the total of the non-mechanical energy by the end. So the graph here at the end of the LOL diagram corresponds probably to the 6th bar graph in the stacked bar graphs below, where we're showing the energy bookkeeping of all the various types of energy. And in the middle, we have this system flow, and what it's saying is our system is essentially consisting of everything except Buffy herself. And Buffy provides the energy to perform the work that moves the balloon in the air. So Buffy is performing work on the balloon that gets this whole process started and makes the energy transfer from one packet of energy to another to another. Okay, so now that we've looked at a fairly complicated example of how energy can redistribute from one packet to another packet, Let's take a look at some more simplified examples using the University of Colorado at Boulder PHET simulation. PHET stands for Physics, Education, Technology, and they created a simulation of a skate park, and they call it the Energy Skate Park. So this is a simulation that shows you how potential energy, specifically gravitational potential energy, and kinetic energy change as a skater goes down the skate track and then back up the skate track. So number one says, according to the energy versus position plot below, see the black dashed line, at which position is the skater? So disregard the picture of where the skater is when you do this analysis. Remember, gravitational potential energy is equal to mass times g times height. Well, the mass of the skater isn't changing. G isn't changing because we're still on Earth. The only thing changing for the skater is h. So the higher h is, the higher the height is, the more gravitational potential energy. And kinetic energy is 1/2 mass times speed squared. Again, the mass isn't changing, so the only thing that changes is the speed. Well, when they're at the top, they don't have speed, they haven't started moving down, but by the time they get to the bottom of the track, they're moving very, very fast. So that's where the maximum kinetic energy will happen at the bottom. So what you typically find is at the top, there's lots of gravitational potential energy, but no kinetic. And at the bottom, there's lots of kinetic energy, but very little gravitational potential energy, especially at the very bottom. And if we blow this graph up just a little bit to make it more obvious, you can see we have this graph here that's plotting 4 different types of energy. In green is the kinetic energy. In blue is the potential energy, specifically gravitational potential energy. The yellow is total energy, and since energy is conserved, you'll notice the total stays constant throughout the time. As time is progressing, it doesn't change at all. And then the fourth energy that's shown here is thermal energy. We're not going to really discuss this. This is only if you set the simulation to include friction, and friction would create heat, which is transferred and becomes thermal energy. And we're not going to be including friction, so the thermal energy will stay 0. This is an imaginary frictionless track. So all of the energy will either be in potential energy, gravitational potential energy, or kinetic energy, or some combination of the two. The higher they are, the more gravitational potential energy. The lower they are, the faster they're moving, and the more kinetic energy they have. So in this particular analysis, they are asking us to look at this point in time. You'll notice initially is over here. Initially, all of the energy is in the form of potential energy because they're very high up. And initially, there's 0 kinetic energy because they haven't started moving yet. But by the time they're at this lined position here, this part, you can see that the gravitational potential energy has decreased, the kinetic energy has increased, and they're now half of the total. They're each half of the total. Well, that tells us they're not at the top, or they'd be all gravitational potential energy. They're not at the bottom. They'd be all kinetic energy and no gravitational potential energy. They must be right in the middle, so they're at position C. And I want to point out to you, the shape of the track is completely mimicked by the shape of the gravitational potential energy plot, the blue curve. So you can tell where you are in the track by where you are in the potential energy curve, and vice versa, based on the height that you're at. Number 2 says, at which position is the skater according to the energy bar graph? All right, so now we're looking at an energy bar graph. We've got, again, 4 different types of energy. We're going to ignore the thermal because this is a frictionless track. So all of the energy will either be in the form of kinetic, potential, or some combination. And the total will always stay constant because of conservation of energy. We are never losing energy. We are never creating energy. We're just interconverting forms. Well, at this point, it tells us there's more kinetic than there is potential, which means they're moving fast and they do have some height, but not a lot of height. Well, the most obvious position that matches that is D, because at D, they've lost most of their gravitational potential, but there's still a little bit. They're still above ground level, so they have some potential energy, some gravitational potential energy, but they have a lot of kinetic energy because they've come down this slope, this ramp, and now they're moving very, very quickly, so they're going to have a lot of kinetic energy. So the answer here is D. Number 3, at which position is the skater according to the energy pie chart? Again, we're going to ignore the picture of the skater and use the energy to determine where the skater is. And you can see from the pie chart, the whole circle represents the total energy, and the blue fraction of this pie represents how much of the total energy is potential energy, specifically gravitational potential energy, and the green represents how much of the total is kinetic energy. And you can see from this pie chart that only a small part of the total energy is in the form of kinetic energy. The vast majority is in potential energy. Well, if the vast majority is in potential energy, that tells you the skater is at a very high position. But there is some kinetic energy, which means the skater is moving. Well, let's think about what kind of pie chart we would expect for each of these 5 positions. At position A, they're at their highest point, so they're going to have a lot of gravitational potential energy, but they're not moving, so there'd be 0 kinetic energy. So that would be a completely blue circle. It would be all potential energy. At B, there is still a lot of gravitational potential energy, but now the skater would be moving at B, and you would expect some kinetic energy. By C, they're halfway down, so half of the energy would be in the form of potential energy, and half would be in the form of kinetic energy. By D, most of the gravitational potential energy is lost. They still have some because they're still above ground level, and they'd be moving very, very fast. So in that case, the pie chart would be mostly green representing kinetic energy and only a little bit of blue representing the potential energy. And then by the time they got to E, this is the bottom of the track, there would be no gravitational potential energy, no blue in the circle, and we would expect a fully green circle because all of the energy would be in the form of kinetic energy as the skater is moving at their maximum speed. Well, which one of these matches this particular pie chart? It's B. B has a lot of gravitational potential energy and a little bit of kinetic. Number 4, which pie chart represents a ball at position 3? Now you can see position 3 is not at the top and it's not at the bottom. It's somewhere in the middle. We would expect it to have some gravitational potential energy, and we would expect it to be moving since it started at the red dot position. And as it came down, it gained a lot of speed, and then as it went back up, it would lose some speed, but gain gravitational potential energy. So the question is, which of these pie charts best matches? Well, it can't be chart A. That's fully potential energy. We'd expect that at the highest points. And it's probably not D, because D is almost all kinetic energy with only a tiny bit of potential energy. And maybe that would be representative of that dot right there, where it's just a little bit above ground level. So there's some potential energy, but there would be a lot of kinetic energy. But we have position 3 here, and this has a significant amount of potential energy and a significant amount of kinetic energy. Roughly similar, but you'll notice if we look at the maximum height and the minimum height right here, and we ask ourselves, how far down are they? Well, they're here, so they would have lost a lot of gravitational potential energy, they would have the gravitational potential energy associated with that height, and the rest would be kinetic, and a little bit more kinetic than potential. So we would expect it to be C. So one of the key points I want you to realize is that you can figure out which pie chart it is by just looking at how high above the ground it is. The higher above the ground, the more gravitational potential energy, the more blue you're going to see in the chart. So small amount of blue means you're very low in terms of how high you are on the track. A large amount of blue means you're very high up on the track. Number 5, if the ball at position number 3 has more mass, how would the pie chart change? The pie chart from the previous question. Well, let's look at the previous pie chart real quickly. We see its answer C, and there is a significant amount of kinetic energy, a significant amount of gravitational potential energy, a little bit more kinetic than potential energy in this question. Well, if we're increasing the mass, think about what that does to the kinetic energy, think about what it does to the gravitational potential energy. The kinetic energy is equal to 1/2 mass times speed squared, and the gravitational potential energy is equal to mass times g, the acceleration due to gravity, times height. Well, you'll notice while we've been talking about how kinetic energy is very dependent on the speed and gravitational potential energy very dependent on the height, both of these are directly proportional to the mass as well. Mass is in both of the formulas, and if you increase the mass, the kinetic energy will increase. If you increase the mass, the gravitational potential energy will increase. So both will increase, and it will not change the ratio of kinetic to gravitational potential energy, but it will change how much total energy is there because we have a new situation with more mass having the same height and the same speed. And that means the whole pie chart would just have to be a bigger circle. So our answer is B. Number 6, as the ball moves on the slide away from position number 3, the kinetic energy bar below on the left side, this graph right here, gets taller. Which way is the ball moving? Now, notice that the question says the ball is sliding away from position 3. It doesn't say whether it's sliding this way or it's sliding up this way. It's just moving away from number 3, moving downward or upward. And we have to figure out which way it's going. Well, we know at position 3, it has this energy bar graph. And what you see is that it's a mixture of kinetic energy and gravitational potential energy with a little more kinetic than potential, which matches the height of position 3 relative to these upper heights where the ball could have started from one side or the other. And the point is we have this much height, so that height will give it a certain amount of gravitational potential energy, and having dropped this much will give it a certain amount of kinetic energy, which in this case is more than the potential energy. Well, let's just remove those for just a second. And the question hinges on what happens to the energies. If you look at what happens to the kinetic energy, it goes up slightly, and the potential energy, the gravitational potential energy, goes down slightly. Well, the gravitational potential energy is the easier one to think about. If the gravitational potential energy is going down, the height is going down. So the fact that this bar is changing to this bar, a shorter bar, means less gravitational potential energy, and that is equal to mgh, which means there must be less height, and that tells us that it's heading towards position 2. Number 7, below is an energy bar graph of a skater. How would you describe the skater's motion? Hint, there is one main answer. A second answer is also likely to be true. All right, possible answers are A, moving at a constant velocity, B, stopped, C, getting slower, D, getting faster, E, at a maximum speed. Okay. Well, if we look at this graph, a couple things should be obvious. The first thing that should be obvious is that all of the total energy is in the form of kinetic energy. There is zero gravitational potential energy. Well, this tells us a couple things. Number one, we envision a track, and it doesn't really matter what shape the track is in. We know that this skater is at their maximum speed because they are at their maximum kinetic energy. They couldn't have any more kinetic energy. They've already maxed out the total energy in the form of kinetic. They also have no potential energy, which means they're at the bottom of whatever track they're on, and they're moving as fast as they possibly can be for that particular track. So we know that they are at their maximum speed because they're at their maximum kinetic energy. But since they're at their maximal speed, they can only get slower. They can't get faster because that's what maximum speed means. They're at their top speed. So they're probably also going to get slower as soon as they pass that point. Number 8, below is the energy bar graph of a skater. How would you describe the skater's height? Well, remember, gravitational potential energy is a key indicator of the height. The higher the height, the higher gravitational potential energy. So we can see from this graph, we see the total energy, and we see it is evenly split between kinetic and potential energy. So we know they are literally in the middle of their drop down to the bottom. So they must be at a position halfway down. So the middle is the answer. Number 9, which energy bar graph shows an object moving the slowest? Well, we know if we're asking questions about height, we look at the gravitational potential energy. But if we're asking questions about speed, we look at the kinetic energy. So the kinetic energy is highly dependent on the speed. The slowest object will have the lowest kinetic energy. Well, if we look at the kinetic energy bar in green, we can see we have a fairly low kinetic energy here, zero kinetic energy here, and a fairly high kinetic energy here. So the lowest kinetic energy means the lowest speed, and therefore the answer is B. And then finally, number 10, which energy bar shows an object moving the fastest? Well, again, speed is indicated by the kinetic energy. We're going to look for the graph with the highest kinetic energy because that's the one that has the highest speed. And clearly the answer is C. And that concludes this video.